Nowadays, with the newer furnaces, and this is pretty much what we're all going to be running into, it's more of a high limit than anything else. So it'll send a signal to the furnace when it gets too hot for the furnace to shut down. You know, the manufacturers of these furnaces and the engineers that went ahead and put all these things together, they know, how long it takes before I heat up my heat exchanger. All right, so whether it's 20 seconds, 10 seconds, 30 seconds, they're going to let the computer now decide, we're going to light the flame. We're going to make sure that the flame is lit. We're going to make sure we're getting some heat and the temperature is rising. So we're confirming that our flame is there. And then we're going to let it go for about 15 seconds. And then we're going to kick on our blower fan. If my blower fan doesn't work and I reach a certain temperature, then the fan limit switch or the high temperature sensor is going to activate and it's going to shut our furnace down. All right. I do expect you to be able, if I had you in front of me with the furnace, on any furnace, to be able to identify the fan limit switch or the high limit sensor on any furnace. Newer units, it's going to be just a rectangular. Sometimes they're black, sometimes they're brown, sometimes they're gray. Older units, they're going to be a dial-up thing. Typically, there's going to be that silver box that's on top of it. That silver box was removed so we could see the inner components of this one here. All right, but most of the time, that's what we're going to run into. All right, different types of drafts. I would like you to know the difference between a natural draft, an induced draft, and a forced draft. All right. The left-hand side. All right. So this furnace over here. Notice there's no inducer fan. So the middle one we have an inducer fan. The right one we have an inducer fan. But the left one we don't. All right. So this one we're going to create a fire at the bottom of the heat exchanger. That heat is naturally going to rise. And that's going to go through my vent connector into my chimney or B-vent or whatever and leave the building. All right. Hot air naturally rises. That's considered a natural draft. There's no mechanical support whatsoever. The second one here is a forced draft. Now we have the same fan that's there. Now that fan is taking air, so our combustion air is coming from the outside. This is going to be under a negative pressure here. And then I'm blowing air into the heat exchanger. So I'm forcing my draft into the heat exchanger. Now I'm going to have a positive pressure inside this heat exchanger. All right. The reason we don't do this anymore is when the furnace is starting up and I have a fire going inside, if that is pressurized on the inside and if there's a hole anywhere on the inside, then I'm going to end up with pushing those combustion gases or the after-fire gases or the carbon monoxide into my circulation air. And depending on how big that opening is and where that opening is, that may happen after the blower fan is kicked on. It will most likely happen before the blower fan kicks on. But if the blower fan is before the heat exchanger, and that creates a positive pressure on the outside and a positive pressure on the inside, whichever fan is stronger is going to cause the air movement to come in there. But if it's at the very top, sometimes it actually creates a Venturi effect as well. All right. So we're really not going to run into too many furnaces that are forced draft. That's going to be on the very early stages of the higher efficiency furnaces. They realized this was a mistake. They realized that this was dangerous. As soon as those heat exchangers failed, then that carbon monoxide was going into the rooms and people could definitely get injured, killed, or whatever. It gets bad. All right. So we don't do that anymore. Nowadays, what we do is what we call induced draft. All right. So on the third one, or the far right one, we're looking at our inducer fan here. That when that's running, it actually creates a negative pressure inside the heat exchanger. It creates a positive pressure afterwards. So now, even though it's a smaller fan and not as powerful as our blower fan, when that burner kicks on and the inducer is going and it creates a negative pressure in there, at least if there is an opening, we're going to have that secondary safety thing where air is going to come into the heat exchanger and not into the circulation air. And then if I have a positive pressure when the blower fan's going, that even makes it stronger of a pressure differential. So the less likely of a chance that comes in there. And again, me saying that, doesn't mean that a crack or a hole in the heat exchanger is okay because we have these pressure differentials. No, it's still not okay. All right. But I just want you to know some of the engineering that was built into these furnaces that makes it safe. So natural draft, forced draft, induced draft from left to right. Natural draft, forced draft, induced draft. Flues, most of the stuff we're going to be dealing with are going to be category 1, 3, and 4. I never really saw a category 2 furnace. That would be a high efficiency furnace or a condensing furnace that either does not have an inducer fan or it has a forced draft fan when we're dealing with it. So I've never really seen one. So most natural draft furnaces, those are going to be category 1 furnaces. Once we put that inducer fan on it, and so we have a blower fan going, and we're going to be creating a pressure difference inside of it, that's what makes the difference between a category 3 and 4. So in other words, 80%ers are pretty much category 3. 90%ers are category 4 furnaces. Plain and simple. This is a natural draft furnace. What are we looking at here? Atmospheric. Burners do not rely on a fan to push the combustion air. Hot air rises. We kind of chatted about that already. So I'm going to move on to the next one. Checking the heat exchanger. As I was saying on the older natural draft furnaces, it was doable. It was difficult, but it is doable. And there's a lot of other tools that we can use nowadays, and you got to decide how deep you want to go into your inspections. All right, and whatever you do, don't be convinced by anybody telling you that it's beyond the standards, above the standards. Our standards of practice that we do is what is written in the IDFPR law in the state of Illinois. So it says we inspect the furnace. We describe it by its fuel source and distinguished characteristics that come in it. But it doesn't say what tools we have to use. It doesn't say how we inspect it or how deep you want to go. None of that. There's many people that will just turn it on and they look at the flame and they say, well, that's a pretty blue flame. And it's and you got heat coming out of it, so I guess it's okay. And they leave it at that. There's other people that put, more expensive equipment on furnaces to check the gases and make sure that everything's tuned right and coming out of there. So you can go everything from a heating contractor to a guy that turns the thermostat on and says, yep, it's making heat. All right, plain and simple. Part of this pressure differentials, all right, I want you to remember, if you think that using a carbon monoxide detector in the circulation air is going to tell you if there's a crack or a hole in the heat exchanger, I'm going to try and convince you that it won't. Okay, I mean, if it's really bad, then it will. If it's so bad that we're getting carbon monoxide making into the house, then hopefully you'll be picking it up that way. But small openings, small cracks, which are still dangerous, they're not going to bleed over into the circulation there because of those pressure differentials. All right, but it's still a dangerous seal. So here's a natural draft one. You can see inside of it, it's rusty, it's dirty. I do have another friend of mine who has a very successful business, and he shared with me that he wants all of his guys to, give some sort of a reason. He knows that if you look hard enough at these furnaces, that they are not perfect by any which way, you can identify a reason to get a heating contractor out there and let them do a more thorough inspection. I think that's a very safe, sound advice. Me, I always wanted to be that guy that's able to give you that more thorough inspection. So go from there. Another natural draft furnace. Everything's open on the inside of this thing. Yeah, I got nothing much more to share. You can see all the rust and corrosion, and same thing going back to this one. You can see how rusty everything is on the inside. But these old natural draft ones weren't. I mean, they're just old. They're just in bad shape. I don't know what much more to say. At this point in time, even if it isn't running safe, I still want my client preparing for a new furnace. All right. So the biggest problem with gas forced air furnace, and the biggest thing that they want us there for, is a crack or a hole in the heat exchanger. And more specifically, if there's a chance that carbon monoxide is getting into the circulation air, which could harm somebody. All right. So there are different methods. There's different things that we could do that are evasive and non-evasive. One of the things people can do is put a carbon monoxide detector. I kind of talked a little bit about this in the circulation air that we breathe. But a crack like this one and the pressure differentials, that probably won't show. Same thing with, let me back up a slide here. Smoke candles. This is something I really don't recommend that you do. But you can actually put a lot of smoke inside the heat exchanger. And if there is an opening in there, that smoke will pass through the heat exchanger as long as the blower fan's not running. And then that smoke might be coming into the house. But, this is somebody else's home. And I'm not a big fan of putting that in there. The magic spray is kind of a joke a little bit, but it is an actual spray. I'm going to show a picture of it because I can't think of the name of it beforehand. But it has a lot of alcohol into it, and it is very flammable. And I've seen it work where it actually showed a hole or a crack in the heat exchanger. So with this spray, with the furnace running and the burner going, you actually put the spray into the blower fan of the circulation air. And when you spray it in there, like I said, it's very alcohol based, so it dissipates quickly. But as it goes over the heat exchanger, if there's any openings in that, then that heat, it's going to blow to the inside of that heat exchanger. And if it's able to touch the flame, then it changes the flame from a blue to either an orange or a bright red. And it's pretty cool when you see it happen. So you spray like 6 pumps in there. And yeah, it goes into the flame. The flame goes from blue to red and then it goes back blue again. The only way for that mist to get there is if it's... for that mist to get there is if we have... a hole or an opening into that heat exchanger. So, and then the other one out here says flame dance. That one I'm not too comfortable with. I mean, you really have to have a big blast of air from that circulation fan blowing on the flame and causing it to flicker and move. It just doesn't happen. So I wouldn't count on that one. All right, so this is an actual crack in the heat exchanger. We're actually looking at 3 dangers. Even though that crack looks very small, when it heats up, the crack opens up. And then where it is, it's going to blow in or out. All right. This one's kind of a no-brainer. If you can't see it, it's down here at the bottom. This, I didn't make a good circle, but that opening down there is rusted through. But even this rust that I see on here, that would be enough for me to say, hey, listen, you got to get somebody else out here. Chances are good this thing's going to be bad. Or you got to use more definitive equipment to see if anything's bad on here. But as long as we could visibly see it, then we know that there's a hole or crack in it. Another heat exchanger, the entire back of it was blown off. And that's a very common. If you notice when I go back straight to the rear of the heat exchangers, probably one of the most common places that they crack or break. We saw it on all 3 of these actually. And then right where the burners come in, right up underneath it, as it comes back, there's a lot of bends in there and high flame impingement in there. I shouldn't say impingement, but there's high heat in there. And those are other areas that crack and get damaged quickly. All right. So carbon monoxide is serious stuff. It doesn't take all that much. When we're measuring these things, we're measuring in parts per million. All right. So when we got 200 parts per million, that's a lot of parts for where it comes into it. So at 200, well, actually 40, we'll get down there. That's usually when the carbon monoxide alarms start going off. And then I think that's also what they call the threshold limit value, the TLV. And that is the amount of carbon monoxide that the EPA has determined to be safe if you're in a working environment. So you could be there 5 days a week, 8 hours a day in that environment. Anything more than that is dangerous. All right. I still think 40 is dangerous. We shouldn't have anything coming over into the circulation air. All right. So here's another natural draft furnace, straight up vent connector. We have a chimney on the other side of that foundation. All in all, everything looks pretty decent. Our vent connector clearance to combustible is going to be 6 inches. The only thing that I see in this picture that has combustible material that's close is going to be my insulation from my air conditioning line set, my drain from my air conditioning condensate drain, that's PVC, and that's really about it. And both of those, I believe, are 6 inches away. This one here, I got a flexible drain. I do believe that's less than 6 inches away. And even if there is no burning, scorching, or anything on there, I'm going to go ahead and start calling that one out too. Another natural draft furnace. So now we have an inducer fan. And one of the questions I get is when they talk about the vents and the vent connectors, sometimes they're metal, sometimes they're PVC. You know, how do I know when it's a high efficiency? What are my clues? How do I know it needs to be plastic? Or how do I know it needs to be metal? And we cannot mix the two of them, all right? And everything goes to the housing, and I'll show you a closer up picture of it in a little bit. But everything goes to the housing of the inducer fan. If the housing of the fan is plastic, then my vent and vent connector need to be plastic. If the housing of my inducer fan is metal, then my vent connector and my vent need to be metal. Plain and simple. All right. And I'll open that up and see. So on this drawing here, this is my inducer fan. But behind this metal plate, you could see this here is all metal. All right. So when this housing around here is metal, that means that my vent connectors and my vents also have to be metal. This is a mid efficiency or an 80% furnace. And that's going to be my one telltale sign that they're just not going to change. All right. So first thing that happens, thermostat calls for heat. We want to turn it on. Then the computer basically checks all of its quick circuits, make sure it's okay. And the first thing the computer activates that we're going to see operating is going to be this inducer fan. So that wheel is going to start spinning. All right. Now the computer doesn't know if the wheel is actually creating a draft or working at all, or the wires are broken, or could be, I've seen birds stuck in these things and they didn't operate either. So if it's working and it's going to be creating differences in pressures, we're actually going to sense for that. So this cylinder device right here is called a pressure differential switch. Now sometimes you will see a tube, either it'll go to the heat exchanger or it'll go to the underside of the inducer fan. And if it's spinning, if it's creating those pressures, then that device will close, sending a signal to the computer saying, yep, my inducer fan is running, it's spinning, I created a draft, you're good to go to the next stages. All right. I do expect you to identify the inducer fan. I'm also going to go back and review a couple things. I'm also expecting you to identify this brown disc down here. And I'm hoping you're thinking that's the high limit switch that comes in there. So right now, we should be able to recognize our inducer fan, our pressure differential switch, and our high limit switch. And I don't care if you call it a fan limit switch as well. Either way is fine. All right, here's our typical, again, mid-efficiency furnace. So my inducer housing fan is made of metal, and my vent connector is also made of metal. Now, if you notice that down here, and this is a typical thing that we see, the vent connector, where it enters the furnace, it shrinks down in size. This furnace was changed out. They put a new one in there, it was more efficient than the old natural draft furnace that was there. So it does send up less BTUs than what's going up on there. These vent connectors and vents are supposed to be sized to this appliance, not to the old one. All right. So whether or not this is going to continue to work, I can't say. All right. But I am going to be looking for signs of condensation on all of these joints. Any sort of dripping or anything that's going to show where I have any sort of bad drafting, and I'm going to be aggressive with it. Right, this is a gas. We do have gas pipes here on the left coming in here. And so we know we have to have a 6-inch clearance to our single wall pipe that goes up in here. And this orange hose that we're looking there, that's what connects my inducer fan to that pressure differential switch. And as long as that fan's spinning, I'll be able to create a positive pressure, and this switch will sense it. Now we get up here and we start seeing that rust stains and the white condensation come back in here. You could actually see some dripping on the very bottom underneath here as well. All right, and so it's actually leaking out of the inducer fan. All that condensation's coming back. This furnace is not venting properly. All right, I should not have that condensation coming in here, and I don't want to take ownership of this problem. We're going to document this, and we're going to push this off to a heating contractor. Same thing, more corrosion, more rust, more dripping. These are all things that we're going to be pushing off to a heating contractor. Sealed combustion units, we're getting into more of a higher efficient furnace when we come to it. Sometimes the only thing you can see on the inside of these things is through that little peephole right in there. So you're just limited on what you could do. All right. Now these plastic or the high efficiency units, that sizing of the vent connectors, they can get bigger or smaller. So that sizing to the appliance is only for the mid efficiency furnaces, not necessarily for these. But we still want to make sure, no, there's not much we can do because they are going to condensate. Liquid is going to come back. They are going to collect it and they are going to drain it. That's what they're for. So I may mention before about bringing combustion air from the inside. So this high efficiency furnace can operate this way if I'm in a wide open basement. Can't be in a bedroom, can't be in a bathroom, can't draw that combustion air from the bedroom or the bathroom. It needs to be big enough, depending on the BTUs that are there, to get enough combustion air. And quite frankly, now I'm taking conditioned air and bringing that to the outside. Let's see what this is here. So any metal vent, not just mid efficiency. Mark, I don't understand what you're asking me there. And maybe I'm going to wait and hopefully you can give me a clearer question when we come to it, and I will address it. Another high efficiency. All right. This way our combustion air is coming from the inside. It's coming from the right-hand side and exhausting to the left. 2 pipes. Again, it is okay to bring combustion air from the inside. We just can't bring it from a bedroom or a bathroom. And the reason for the bathrooms is for the moisture. And from the bedrooms, I think they're afraid of backdrafting and combustion air coming in there. All right. I do want you to know the term backdrafting. I think I used flame rollout already. I've used scorching already. Size changes should be avoided. I'm going to bring that back up here again. Thank you for rewriting that. All right. So size changes should be avoided for any metal venting to avoid corrosion. Exactly. That's the point I was trying to make. Yeah, because anything where we're going to go ahead and collect that condensation, if we don't get a good draft coming out of there, it should be smooth. The only time we're going to have a size change is if we add another appliance to it. So if I go from 1 furnace to 2 furnaces or 1 furnace to a furnace and a water heater, then it will get bigger. All right. But that should be the only time, Otherwise, it will go ahead and reduce it. Alrighty. So backdrafting. On natural draft furnaces, typically on induced draft furnaces, we're not going to have any sort of backdrafting issues. It's just not going to happen. The fans themselves are going to go ahead and make sure that everything gets out of there. If I can't build up the pressure and I can't get the airflow, hopefully the sensors are happening. So it's not impossible that it'll happen, but the chances are very slim that it could happen. Backdrafting is mostly going to be found on natural draft furnaces. All right. So here we have our burners. This is where our combustion air goes in. Our dilution air comes in at the draft hood. So our flame goes in here. We create our bad gases inside the heat exchangers. They group up again and send those bad gases up and out the vent. I have to mix dilution air in with it in order to clean it up, basically, or cool the temperature down so it doesn't move too fast. If there's a blockage in this vent connector, if it has a thermal barrier somewhere in the chimney, then I'm going to start backdrafting. Now with these, I am going to tell you that backdrafting is normal. All right, when they first start up, you are going to backdraft until it gets built up enough heat to get that draft and get it started. You are going to have some, but if it's over a minute and it's still backdrafting or continuously backdrafting, that shouldn't be happening. All right, a little bit in the beginning for a short period of time, that's actually normal. All right, but if it goes on for a long time, that's not normal. Where it comes with it. Different ways that we could check for backdrafting. Those of us that wear glasses, I usually take the glasses and I'll put it in front of the hood, and if it steams up, it's backdrafting. I've seen where you could take a flashlight and shine the flashlight on an angle on the beam, and then you give a quick blow of air and get the dust up in the air, and you should be able to see that dust going up the vent connector instead of coming down and into the room. Those are also another signs of backdrafting. Typically, you're going to end up seeing rust, and I know I got a picture, rust and scorching on the draft hood here. So just different clues where it comes with it. All right. This is an old natural draft furnace, and you could see the big orange scorching that's right there. This thing has been backdrafting for a long, long time, and all the moisture that comes from the fire has been causing that. I don't know what much more to say. To this is a no-brainer. We actually have scorching on top of the burner draft hood itself, so you can see where not only was it coming out of there, but it was also flowing upwards as well. Just a closer picture of everything. So what we started doing for safety features is they started putting backdraft sensors on these things. And they're nothing more than heat sensors, all right? This is an aftermarket one on a hydronic boiler that's on there. And so that if the heat is coming down and in, that this is going to sense that heat and it's going to shut our boiler off, all right? We actually started putting these on the furnaces as well, so you can see where that little arrow is pointing at. That's going to sense for the backdrafting and again shut everything down. And there's a close-up of that. Nothing more than a heat sensor on there.